Welcome to Lecture 2, Units, Energy, and Methods of Heat Transfer. So, in this lecture, we will be getting into part of Chapter 2 in the Ahrens book. The reading that corresponds to this lecture, as you can see, is pages 26 through 36 of Chapter 2. And we're going to start talking about units, because this is a science class. After all, this fulfills your physical science B1 requirement. And math is the language of science, so we'll be doing some calculations. And we're going to be talking about a lot of variables in this class. Okay, we already talked about some of them. Temperature, humidity, wind direction, speed. And when we want to describe a variable using numbers, in other words, give a quantitative representation of a variable, we need to include units, because if you just say the temperature is 40 degrees and don't specify whether that's Fahrenheit or Celsius, or the wind speed is 12, okay, is that miles per hour, is that knots, is that meters per second? It's very important to always include units when you talk about numbers corresponding to variables in science, okay? So we'll be familiar with some important units and how to convert between them. Then we will start talking about energy. What is energy? And then get into methods of heat transfer, or basically energy transfer in our atmosphere. Okay, so let's start talking about units. We will be using both metric and English units. Now, do you know which of these systems, the metric or English system, does the United States still use as its official system for measurements? US uses the English system. And for the world, that's very rare. There are a few hundred countries in the world, probably over 300 now. And of all the countries in the world, only 3, okay, a very tiny percentage of all the countries still use the English system as their official system of measurement. Most countries have switched over to the metric system, okay? US is one that still uses the English system for official measurements. Not to say some people don't use metric units, but that's our official system of measurements. That's the one you see more commonly. So US is one, and the other two are Liberia in Northwest Africa, and Burma, also known as Myanmar, in Southeast Asia. It happens to border Thailand, okay? Where you're in some places there, like Bangkok, you can really turn up, okay? So, most important units we will be discussing include those for distance, kilometers and miles, okay? Kilometers is a metric unit for distance, whereas miles is an English unit of distance. And you might already be more familiar than you think about converting between the units here. If any of you have ever run a 5K race or a 10K race, you might know that those distances correspond to 3.1 and 6.2 miles respectively. Temperature has the metric unit of degrees Celsius, so the C stands for Celsius, but the English unit for temperature is degrees Fahrenheit. Some people still call degree C degrees centigrade. That used to be a more common name, but generally now it's usually degrees C means degrees Celsius. And so we want to be able to convert between these units. There's a lot of countries in the world, and we start talking about exchanging weather data between these countries and sharing information. It's important to be able to convert between different units, okay, depending on what system the country prefers. Just like, we have to be able to communicate in terms of different languages, being able to translate. So here are our first conversions for going between kilometers and miles. 1.6 kilometers is equal to 1 mile. So 1.6 kilometers is equal to 1 mile. So what you see is that 1 mile is more than 1 kilometer. Okay, if you look at that first conversion factor. And then precisely 1 kilometer is 0.62 miles. Okay, so for the race analogy, 5 kilometers would be 5 times 0.62 miles, or 3.1 miles. Now, converting between different units for temperature is a little more work than just a multiplication or division, but it's still very very easy to know how to do. Okay, here is the conversion between degree Celsius and degrees Fahrenheit. This is if you're given a temperature in degrees Celsius and you want to find out the corresponding value in degrees Fahrenheit. What you do is take your value of degrees Celsius, multiply by 9 divided by 5, 9/5, or if you prefer the decimal form, that's 1.8. And then once you've done that multiplication, you add 32. Okay, notice the addition of 32 is outside the parentheses where you multiply the 9/5 and degrees Celsius. Okay, that'll give you the temperature in degrees Fahrenheit. Let's say you want to go the other way. You're given a temperature in degrees Fahrenheit and you want to find the temperature, corresponding temperature in degrees Celsius. Okay, well, if you wanted, you could do some algebraic manipulation, right, which you've all learned in high school, and solve for degrees Celsius. Or you could save a little work and just look at the next bullet point. I have it for you. You do the work, you'd find that degrees Celsius is equal to degrees Fahrenheit minus 32. And then once you've done that, once you take your temperature in degrees Fahrenheit, you subtract 32, then you multiply by 5/9. Okay? So the order of operations for these conversions between temperatures is very important. There's a reason that you have parentheses. Okay? So if you're going from Celsius to Fahrenheit, you have to do the multiplication first, then addition. If you're going from Fahrenheit to Celsius, you have to first do some subtraction and then multiplication. Okay? And you know, it's interesting because depending on where we were raised, we have an intuitive feel for units, such as for temperature. So many of us Americans, you know, we're used to thinking of temperature in terms of degrees Fahrenheit. And when we have an intuitive sense of, say, how hot 90 degrees Fahrenheit feels. But for many of us, if someone said, oh, the temperature is 30 degrees Celsius, let's say, we might not have the same gut understanding about how that feels and how we should dress, how much or how little clothes we should wear, what color clothes we should wear, okay, whether we might want to bring a fan or, you know, put the AC on if we're indoors and so on, okay? But San Jose State University is a very diverse campus. There are a lot of students who are children of immigrants, one or both of their parents, and there's a lot of international students who are themselves from other countries. And if you're from another country or have parents that are, chances are you're familiar with the metric system. Maybe not so much if your parents are and you were completely raised here, but definitely if you're from a country like China, India, Vietnam, okay, an international student, you probably grew up with the metric system. If you ever watch international news, weather reports, okay, or different countries' weather reports, you'll see the temperatures, the high and low temperatures on the weather map given in degrees Celsius, okay? You also might have noticed how in other countries the speedometers, right, are in not miles per hour but kilometers per hour as the major one, okay? For a lot of cars in America, there will be a secondary unit of kilometers per hour, but it will be in smaller print, okay? It's reversed for other countries. For other countries, the speed limit, posted speed limit, will be in kilometers per hour, not miles per hour, with the exception of Burma and Liberia, okay? But we'll see if they switch over and to the metric system. And Can you think of any advantages of using the metric system over the English system? Look at the prefix here in this distance unit, kilometers. What's kilo mean? Okay, it means 1,000. So how many meters in 1 kilometer? Well, 1 kilometer is 1,000 meters. So 1,000 meters in 1 kilometer. Okay, 100 centimeters in 1 meter. 1,000 millimeters in 1 meter. The metric system has some nice conversions to do between different units of certain variables. Okay, if you're going to smaller or larger units. But for the English system, continuing on with distance, the conversions aren't as intuitive. For example, there's 12 inches in 1 foot, 3 feet in 1 yard, 5,280 feet in 1 mile. Okay, these are some, weird numbers, right? Where are these numbers coming from? Okay, they're not just in powers of 10 like the metric system. Okay, let's have some practice with units now. So, here's a picture of San Jose from the south. So this is the skyline of the largest city by population in Northern California. You can see, if you look closely, CVB. You can see that building on Santa Clara Street, east of most of the skyline. It's at about, East Santa Clara and 17th or so, North 17th Street. You can see a lot of trees in the neighborhood south of downtown. So, and then here's a map of California. Okay, California shown in yellow, Nevada in green, Oregon in just a very extreme southern Oregon in kind of a lighter green, Mexico in orange. So here's a problem for you. Numero uno. On Thursday, September 1st, 2016, the high temperature in San Jose was 75 degrees Fahrenheit. So this video is being recorded on Friday, September 2nd. So yesterday, the high temperature in San Jose was 75 Fahrenheit. Pretty pleasant. It was a little warmer in South San Jose and East San Jose, as often is the case, because those areas of San Ho are further from water, okay, or farther from water. The water helps moderate the extreme heat in the summer. What is the value of that temperature in degrees Celsius? Okay, so you're given a high temperature in degrees Fahrenheit, and you want to convert to degrees Celsius. So what you'll do is use which of these two temperature conversion formulas? The second. Because the second one tells you, if you're given a temperature in degrees Fahrenheit, what the corresponding temperature in degrees Celsius is. So, would like you to work that out, okay, using the formula. And don't just Google the answer or that, because it's important to know these conversions. Because this could appear on quizzes, not quizzes, but tests. This could appear on the final. Okay, you could have homework where you have to show your work. Actually, you will have homework where you have to show your work for the conversion to understand how to use the formula. Because it's important to know the formula in case you don't have access to, say, Google, the internet, or what have you. So work it out. See what you get. Should get a value of 23.89 degrees Celsius. That's rounding to the nearest hundredths place. The answer is 23.8 repeating. The 8 would have that horizontal bar, meaning a repeating number. Okay. Second practice problem, or practice question, if that sounds more inviting to you. California, the golden state, also the green state environmentally. Nowadays, over a quarter of our electricity generation comes from renewable energy sources, much higher than a higher share than the U.S. as a whole. Well, the state's about 800 miles long from Oregon to Mexico. Okay, so if you drive along 101 or 1, or in some places both, so basically, a lot of the coast, 101 runs along a lot of the coast, and some parts of California, the 1 runs right along the coast and 101 is further inland. And in some stretches. They are both part of the same highway or road. You travel 800 miles, going all the way from about Crescent City to the Mexico border, just south of San Diego, and San Diego southern suburb in Tijuana, Mexico. How many kilometers is that? Okay. So, which conversion factor would you want to use? You'd probably want to use the first one, because you might remember this from high school, but you want to try to use a conversion factor where your original unit cancels and what's left is the unit you're trying to get. So you'd write out 800 miles, in parentheses, times 1.6 kilometers over 1 mile, and then your miles would cancel out, and you'd be left with kilometers. And if you do that math, you will get 1,280 kilometers. Okay? Now, an important point to emphasize is that converting changes in temperature or differences in temperature from one unit to another has a slightly different procedure than converting absolute or actual temperatures. So, here are the specifics about this. To convert a change in temperature from one scale to another, you only have to do the multiplication, the 5/9 or the 9/5. You actually don't need to add or subtract. So if you want to convert a change in temperature from Fahrenheit to Celsius or vice versa, actually you don't even have to worry about adding or subtracting 32. You just have to multiply by either 5/9 or 9/5. Okay? So as an example, you see here, triangle 2 degrees Celsius. What does that triangle mean? If you remember from your math, it means change in, delta. So that's a change in 2 degrees Celsius. And this is a really important value for temperature change when we talk about global warming. Kind of the best case scenario for the 21st century global warming is that we keep it below about 2 Celsius, or keep it to a minimum of 2 degrees Celsius. Maybe we could get a little lower, okay? And this is a really critical temperature increase, because this is kind of seen as a tipping point. If the 21st century global warming, so the increase in temperature of the planet from 2000 to 2100 is more than 2 degrees Celsius, the effects on society and people and animals and plants and civilization as a whole could be a lot more detrimental than if, say, the temperature increase is 1.9, 1.8 degrees Celsius. Okay, so there's really a lot of push to try to from countries to try to keep the 21st century warming below this value. Now the thing is, we'd like to understand how many degrees Fahrenheit that is, because we're Americans, right? We think in terms of degrees Fahrenheit. So, what are you going to do if you want to convert it? Well, you're going to use that formula to convert from degrees Celsius to degrees Fahrenheit, except you don't have to add 32. So you only have to multiply the change in 2 degrees Celsius by 9/5 or 1.8. And if you do that, you'll get the change in 2 degrees Celsius corresponds to a change of 3.6 degrees Fahrenheit. We will talk more about global warming as we continue in the class. But just so you know, from 1915 to 2015, so over that 100-year period, the world's temperature went up 0.97 degrees Celsius or 1.75 degrees Fahrenheit. Okay. So the world's temperature went up nearly 2 degrees Fahrenheit in that 100-year period, but in the 100-year period of the 21st century, temperature is probably going to go up at least to 3.6 degrees Fahrenheit, if not more, maybe several degrees Fahrenheit. Okay. What does temperature mean? Question. What does temperature actually mean physically? Okay. On a molecular level, let's get small. So, yes, it describes how hot or cold it is, right?
dictate so many decisions we make on a daily basis, from what we wear, to how much energy we use, okay, to our mood, to what we eat. But what's it actually describing? Okay? Temperature is the measure of the average kinetic energy in a substance. Okay? How fast the atoms and molecules are moving. Air is a mixture of countless billions of atoms and molecules. If they could be seen, they would appear to be moving in all directions, darting, twisting, spinning, colliding with one another like an angry swarm of bees. Close to the surface, each individual molecule would travel about 1,000 times its diameter before colliding with another molecule. And we'd see that not all the molecules are moving at the same speed. Some are moving faster than others. Kinetic energy is also known as the energy of motion. And the temperature of the air or any substance, it could be a fluid like water, is a measure of the average kinetic energy. Okay? Basically the average speed of the atoms and molecules. Molecules are bonds of groups of atoms clustered together. Okay? The higher the temperature, the faster the average speed of the molecules. The lower the temperature, the slower the average speed of the molecules. So let's say we examine a volume of air at the surface about the size of a large flexible balloon, shown here. And let's say the air is initially cold. If the air is warm, the molecules would move faster, and they'd move more apart. They'd acquire greater spacing, as you can see here. The air becomes less dense. Okay? Conversely, if you cooled the air back down, the molecules would slow and the air would become more dense. And this molecular behavior is why in many places in your Ahrens book, surface air can be referred to as warm and less dense or cold and more dense. Air is, as you recall from chapter 1, about dry air by volume is about 78% nitrogen and 21% oxygen. And recall that nitrogen and oxygen exist in diatomic forms. The individual nitrogen and oxygen atoms get lonely by themselves, so they bond with another nitrogen or oxygen atom respectively. What do you think these green molecules here represent? Notice that there's more of them than any other molecule. Those are nitrogen. The red molecules are oxygen molecules. Okay? And then if you look closely, see this molecule here with one red atom, that's a nitrogen atom, and two smaller white atoms. Those are hydrogen atoms. So two hydrogen atoms and one red oxygen atom. I might have said nitrogen. Sorry, that's oxygen. What's two hydrogen atoms and one oxygen atom make up combined? H2O. Water, right? And if you look closely, the geometric structure of the water molecule, and this is probably a water vapor molecule because we're talking about air, which is a mixture of gases. It looks like Mickey Mouse, okay? Now, keep this concept of the definition of temperature at a molecular level in your brain as we go forward to the next slide. Let's start talking about familiar temperatures, and let's not only talk about the temperature scales of degrees Celsius and degrees Fahrenheit, but Kelvin, which some of you may have heard of. You may have used in chemistry and physics problems. Okay? So, looking at this figure, here are some familiar temperatures. The boiling point of water at sea level, not say Coors Field, but at sea level, is 100 degrees Celsius or 212 degrees Fahrenheit. So when you put water into the pot or pan and put the burner on, put the pan or pot on the burner and heat the water up to make tea or ramen or what have you, and when those molecules start, the water liquid molecules start bubbling and boiling, that means the temperature of the water is at least 212 degrees Fahrenheit. quite hot indeed, which is why you wouldn't want to put your hand in the water, right? It would burn. Your nervous system would send you a signal via pain that it's too hot and that it's dangerous via pain. The highest temperature ever recorded on planet Earth was a staggering 134 degrees Fahrenheit at Death Valley, California, in July of 1913, about 103 years ago. Okay. You've probably all been in temperatures of over 100 degrees Fahrenheit outside, that is in the air, maybe much hotter in a sauna, but some of you have been in hotter temperature than others, okay? Typically, in a lecture class, I'll ask, the hottest temperatures students have been in. I'll ask, have you been in 105 degrees Fahrenheit, 110 degrees Fahrenheit? And some have been in temperatures of upwards of 105, 110, even 115 degrees Fahrenheit. And when I ask where, common responses include Palm Springs, okay, in the desert, east or northeast of LA. Las Vegas, popular tourist spot, right? Very hot there in the summer. The southern half of Arizona, the Sonoran Desert, okay? And by the way, remember how weather is the state of the atmosphere at a particular place and time, whereas climate represents a long-term average of weather, including the extremes. A skeptic of global warming might look at this record high temperature in Death Valley and say, how can global warming be happening when the warmest temperature on Earth occurred over 100 years ago? Well, I have a question for all of you. Is this an example of weather or climate? Okay? Is this high temperature on one day, okay, in 1 year at one location climate? It's not. When you start talking about climate, you have to be looking at least tens of years of data. And remember, our climate is more geographically broad, okay, than just weather at a certain place. The average body temperature is 98.6 degrees Fahrenheit. You all are quite hot inside, literally, right? The average room temperature is 68 degrees Fahrenheit. Some people like it a little warmer. Some like it a little cooler. I've read that the best sleeping weather or sleeping temperature is between about 61 to 68 degrees Fahrenheit. If it's a hot day and you don't have the AC on, you're environmental, or you don't use it, and it's above this, and it remains warm at night above the 70s, or in the 70s in your room, it can wake you up. And conversely, if it gets too cold, the temperature in your room starts dropping into the 50s, that can wake you up as well. Okay. The freezing point of water at sea level is 32 degrees Fahrenheit, 0 degrees Celsius. We all know that probably. San Jose, several days a year, nights a year in the wintertime will get below this value. Sometimes years more than others. Here's a bitter cold day, around minus 15 degrees Fahrenheit. Yeah, and I was talking about the highest temperatures ever, that you've experienced. And I mentioned the lecture class. Well, you've all completed that discussion activity, the first lecture discussion, talking about highest and lowest temperatures you've been in. And for the highest temperatures, some responses included overseas, some included the Central Valley, some included the deserts of California, Nevada. And you know what's interesting for the lowest temperatures, where they occurred? A lot of people said Lake Tahoe. Get that a lot. So, yeah, that kind of makes sense, because Lake Tahoe is a popular vacation spot for us Northern California people. It's a short trip, it's close by, and a lot of people go in there in the winter to ski, to snowboard, just to be in the snow, and it can get quite cold there. Lowest temperature ever recorded in the world was at Vostok Station, Antarctica, where some research scientists live, in July of 1983. The mercury in the thermometer dropped to an unimaginable minus 129 degrees Fahrenheit. Wow. Oh! Wait a minute. July of 1983 is when the lowest temperature occurred? I thought it's summer in July. Well, in what season is it in the northern hemisphere in July? Summer. What season is it in the southern hemisphere in July? Winter time. We'll talk more about this when we talk about the seasons coming up soon. Okay. Question. What does 0 Kelvin mean? Okay. One thing you might have noticed already is that to convert between degrees Celsius and Kelvin, you just have to add 273. So for example, 0 degrees Celsius is 0 plus 273, 273 Kelvin. But let's say we went cooler and cooler. As, let's say we're talking about air, could be air, okay? As the temperature of the molecules continues to drop lower and lower, the speed continues to get slower and slower. What if we were going to cool air to the point where the molecules were no longer moving at all? They were still. They had no vibrational movement. Do you know what temperature that would correspond to? 0 Kelvin, because Kelvin is an absolute scale of temperature. And 0 Kelvin is the lowest theoretical possible temperature in the universe. There can't be a temperature of less than 0 Kelvin, because then the meaning of temperature would break down. Temperature describes the average speed of the molecules. Well, there's nothing slower than not moving at all, right? There's not like negative speed. I mean, you could talk about speed negatively in terms of the direction, but the molecules can't be moving slower than not moving at all, right? So that's the lowest possible temperature. If you do the math, it's minus 273 degrees Celsius. It's about minus 459 degrees Fahrenheit, okay? And if you're interested, that's possible in the universe, but in labs, scientists have never been able to get anything all the way down to 0 Kelvin. They've been able to get some elements down to within millionths of a degree Kelvin, but not all the way to 0 Kelvin. Not all the way turned down for what, okay? Now, we're getting familiar with temperature, and we're talking about energy. And you know what? Kinetic energy. And you know, for temperature, and you know what? Heat is a form of energy. Heat is energy transferred from one object to another because of the temperature difference between them. So the atmosphere contains internal energy, the total energy stored in all the molecules, but heat, on the other hand, is energy in the process of being transferred from one object to another because of a temperature difference between them, okay? And after the heat's transferred, it can be stored as internal energy. Latent heat is a hidden type of heat. This is very important when we talk about cloud development and thunderstorms and atmospheric instability. You see, water vapor is an invisible gas that becomes visible when it changes into larger liquid or solid particles. I want you all to know that you can't see water vapor. So when you see a cloud, you're not looking at water vapor. That's invisible. Clouds are made up of either liquid droplets and or ice crystals. So when water vapor or moisture in the air turns into liquid droplets, condensation, or ice crystals, deposition, it can form, and great enough amounts, it can form clouds. And the transformation from one phase or state of matter to another is called a change of state or a phase change. Okay? How many states of matter are there for substances? There are 3. Solid, liquid, and gas. And when something, whether it be water, whether it be air, whether it be carbon dioxide, okay, changes state from one to another, it takes energy, or energy is given off. The energy, that's a form of heat required or released during a phase change of a substance, is called latent heat. You might be wondering why it's called that, latent or hidden heat.
Well, here's an example to help you understand that. The cooling produced by evaporating water. If you examine a small drop of water, you'd see at the surface there's molecules constantly escaping, evaporating. Not, like we said, temperature is only a measure of the average kinetic energy of the substance. Not all molecules are moving at the same speed. Some are moving faster than others, and the fastest moving ones, the most energetic molecules at the surface of a drop of liquid water, or aqua, some of them have enough energy to break the surface tension of the water and escape it and go into the atmosphere as vapor, evaporate. Because the faster moving molecules escape most easily, the average motion of the molecules left behind decreases, okay? Because think about it. During evaporation, the fastest moving molecules will leave, break away, and so the leftover molecules, the average speed of the leftover molecules will be lower because you took away the fastest moving ones. Therefore, the temperature of the leftover molecules decreases. The water cools, basically, because the fastest moving molecules escape the surface tension of the liquid water. Hence, evaporation is a cooling process. And the reason that the heat is latent or hidden is that it shows up after a phase change, okay? So so once the evaporations happen, this hidden energy that was released can show up. You can sense the loss of it, the loss of heat after the phase change, but only after the phase change has happened. Okay, you're not going to sense the latent heat until after the phase change. Okay, evaporation is a cooling process, right? If it's a hot summer day, how does your body cool off? Evaporation, okay? And by the way, we'll talk more about this when we talk about humidity concepts. But if there's more water vapor in the air is juicier, moister, higher humidity, rate of evaporation of sweat on your skin lowers. Because the more water vapor in the air, the slower the rate of evaporation of your skin of sweat. Therefore, more sweat builds up, less evaporates over time, so you don't cool off as fast. Okay, and you feel, hotter and stickier. But if it's drier, the less water vapor in the air, at a given temperature, let's say we're talking about constant temperatures, if we decrease the amount of water vapor in the air, drier, okay, dry heat, some of you guys have talked about in the first discussion activity in reference to highest temperature you've experienced, water evaporates faster because there's less water vapor molecules in the atmosphere, and so it's easier for liquid molecules to evaporate and become vapor and transfer to the atmosphere. Therefore, the drier the air, the faster the rate of evaporation, the quicker you cool off. There's a reason, therefore, as you can see, one usually would prefer a dry heat at a given temperature to a humid heat at a given temperature. Okay? Evaporation is a cooling process because the energy needed to evaporate the water to change its phase from liquid to gas comes from the environment. And the energy lost during evaporation can be thought of as carried away or stored away by the water vapor molecule. It's hidden, and we call that locked up energy, latent heat. The heat energy could reappear as sensible heat, that is, the heat we can measure and with a thermometer and feel when the vapor condenses back into liquid water. What is the opposite of evaporation? Evaporation is a phase change from liquid to gas. And we've been talking about vapor a lot. You see, folks, for water, H2O, we have distinct names for the solid, liquid, and gas states. What do we call the solid state of water? Ice. What do we call the liquid state of water? Water. Ha ha ha. Or liquid, okay? What do we call the gas state of water? Vapor, okay? What's the opposite of evaporation, though? If evaporation is the phase change from liquid to vapor, the opposite of that would be the phase change from vapor to liquid. And what's that called? That's called condensation. That's the opposite of evaporation. Okay? Again, vapor changes into liquid. Now I have a question for you. Remember how evaporation was a cooling process, or is a cooling process, I should say? Okay. What about condensation? Is condensation a cooling or warming process? What do you think? It's a warming process. Now, I wouldn't be surprised if most of you said that, just using logic that, well, because evaporation is a cooling process and condensation is the opposite of evaporation. Sorry, evaporation is the opposite of condensation, or vice versa. So the opposite of a cooling process, you might be thinking, well, it's the opposite of a cooling process, so therefore it's a warming process. Okay? And that's right, but how would you explain that? I mean, it's correct that condensation is a warming process, but how would you explain that? Well, to help you understand and explain why a phase change from one state to another is a warming or cooling process, it's really helpful to have this visual diagram here. And this is from the book. A lot of great figures and diagrams in the book. This shows the 6 phase changes that exist. There are 3 states of matter. Solid, for water we call that ice. Liquid, for water we call that water or liquid. And gas, for water we call that vapor. And as you go from left to right on this figure, you're going from lower to higher energy state. Okay? As you go from right to left, you're going from higher to lower energy state. And I'll come right back. But the way to visualize that is by thinking about the molecular, basically the activity of the molecules for the different states. So here's the states of matter molecular level. In a solid, the molecules are tightly packed, as you can see, usually in a regular pattern. So notice that in the solid here, these green balls are supposed to represent molecules. Notice how they're in a very organized pattern. Okay, clearly see that. In a liquid, the molecules are close together still, but they're not in a regular pattern. Okay, so notice that they're still close together, but they're not. There's not this very clear, organized pattern. Okay. Finally, in a gas, the molecules are well separated. Notice how much greater spacing there is in a gas than liquid or solid. See how the molecules are much farther apart? Because they're moving faster, so they have greater spacing, and there's no regular arrangement. In addition, in a solid, the molecules, they're vibrating, okay? They don't generally move from one place to another relative to each other. In a solid, the molecules are generally moving, they're all moving at the same speed in the same direction. That's why they don't move relative to one another. That's not the case in the liquid. Okay? In the liquid, even though the molecules are close together here, they are vibrating, they're jiggling, sliding past one another. Okay? They are moving in different directions relative to one another. And then in the gas state, independent motion is even more extreme. Okay, so they are moving very freely at high speeds relative to one another, and they're moving faster than in either solid or liquid. You can really get a sense of the speeds of the molecules in the 3 states of matter by looking at this nice animation here. Okay, so here's solid. Notice the very geometric organized pattern, and yes, they're moving, but they're moving with respect to one another.
They're still close together in the liquid state, but they have their own individual motions. And in the gas state, they're moving even faster, and there's a much lower density because they're moving faster, so they have much greater spacing. Okay. As you go from left to right in this figure, you go from a lower to higher energy state. As you go from right to left, you go from a higher to lower energy state. And you can probably now understand that since you've looked at the geometric representations of the states of matter. Okay, I think you from those slides, you can get the sense of how obviously there's of the three states of matter, gas has the highest energy of the three. Okay, the molecules are moving fastest, they have greatest individual spacing, and the liquid is the lowest, the solid is the lowest energy state of the three because the molecules are moving slowest. They have the lowest individual separation and relative independence. Okay. So now, between the three states of matter, there are a total of 6 phase changes. You're probably familiar with at least 4 of them. You probably know the names of these 4. You might or might not know the names of 2 more. Okay, that rhymes. Okay. So, the phase change from ice to liquid is melting. Okay, like when the temperature, the snow's falling, the temperature warms above freezing, and the snow melts. Okay. The opposite of that, liquid to ice, is freezing. Okay, like when liquid water freezes on a cold night. So during melting, would energy be released or taken from the environment? Because it's going from left to right, lower to higher energy state, heat energy is taken from the environment. Think of it this way. In order to go from a lower to higher energy state, there has to be an increase in energy. And that energy has to come from somewhere. It's taken from the environment. It's taken from the surrounding environment or the atmosphere. Okay, that's where it comes from. That's why when you go from a lower to higher energy state, it's a cooling process. It removes energy from the environment. Going from liquid to ice now, freezing. Well, that's going from a higher to lower energy state. As you can see down here, heat energy is released to the environment when you go from a higher to lower energy state. Think of it. If you're going from liquid to ice, the energy state's decreasing. So now that energy is released to the environment. Okay, in order to go from a higher to lower energy state for water, that excess energy has to be removed. Okay, from the individual water molecules. Okay, and it's removed. It's released. It's removed from the water molecules and is put into the atmosphere. So then that adds more energy to the environment, and that's why it's a warming process. That hidden heat is released to the environment. Evaporation and condensation, we've already defined those. They are cooling and warming processes, respectively. Now, sublimation is the phase change for water from ice to vapor, or for any chemical from solid to gas. And you might be familiar with this. If you ever put ice cubes, or maybe one really large ice cube in the back of your freezer, you could do this. If you haven't, let it sit there a long, long time. Over time, you might notice the ice cube becomes smaller. And that's because some of the molecules in the ice state have sublimated and gone into the air in the freezer as vapor, and that's caused the ice to become smaller. Okay, but there was no melting. Okay, instead, sublimation is a direct change from ice to vapor for water. It bypasses the liquid state. Okay, deposition is the opposite of sublimation, where vapor turns directly into ice. Okay, so instead of the water vapor condensing into liquid and then freezing to ice,
the vapor goes directly into ice, and this releases energy. Okay, whereas sublimation needs energy to happen, so it cools the environment. Deposition warms the environment.